Hey guys, welcome back for another chemistry lesson. Buckle in, because unfortunately this is a long one. We're going to talk about electron configurations and the periodic table. So electron configurations allow us to talk about where our electrons exist within the atom. Right? So the quantum mechanical theory describes the behavior of electrons in atoms. We know that our electrons exist in orbitals. And so a description of the orbitals that are occupied by our electrons is called the electron configuration. It basically is like a seating chart for all of the electrons that are in the atom. Right? So what we have in each one of these electron configurations, for each portion, we get the principal energy level, what orbital it is, and how many electrons are in that orbital. All right, so Schrodinger's calculations for multi-electron atoms cannot be exactly solved. As I mentioned in my video about the quantum mechanical model, it's more of a probability than anything, but we can, give a little bit of approximation here. But the reason it can't be exactly solved is because there are things like electron-electron interactions that affect that. So, additional concepts that affect these multi-electron atoms are electron spin and sublevels. So Stern and Gerlach did an experiment that showed that a beam of silver atoms is going to be split into two by a magnetic field. And so what that showed us is that electrons spin on their axis. So as they spin, they generate a magnetic field, and that's because spinning charged particles, electrons have a charge, generate a magnetic field. So if there's an even number of electrons, about half the atoms will have a net magnetic field pointing north, and the other half will have a net magnetic field pointing south. So we can include electron spins in our electron configurations. I'm using air quotes because we don't call it that, but we can include that information, and we do that through orbital diagrams. So what we often do is represent an orbital as a square, and the electrons in that orbital are represented by half arrows, right? So the direction of the arrow represents the direction of the spin of the electron. So this in a hydrogen atom would be the 1s orbital containing one electron with an up spin. Right? There is a rule called the Pauli exclusion principle that states that no two electrons in any atom may have the same set of 4 quantum numbers. Therefore, no orbital can have more than 2 electrons because they have to have opposite spins. There are only 2 kinds of spins. And if the orbital has to have 4 different quantum numbers for the electrons in it, spin being one of those quantum numbers, then if there's only 2 options, there can only be 2 electrons in there. So, knowing the number of orbitals in a sublevel allows us to determine the maximum number of electrons in the sublevel. The S sublevel has 1 orbital, so it can hold 2 electrons. The P sublevel, because we've talked about this, and I'll link in the cards the video where we talked about the orbital shapes, but the P sublevel, we get 3 of those orbitals, so each one can hold 2, that's a total of 6. D sublevel has 5 orbitals, so it can hold 10 electrons, and then the F sublevel has 7 orbitals, so it can hold 14 electrons. Alright, so think about the quantum numbers like tickets to a concert, right? There cannot be 2 people that have the exact same concert ticket, right? Now, we might both have tickets that are row 1 because we're big fans. Row 1, like section A, row 1, seat 5. We can't possibly be there at the same time. So maybe your ticket is for Friday night and mine's for Saturday night. So somewhere in my quantum numbers, there has to be a difference. So in the case of the electrons in a helium atom, for example, they're both in n equals 1, they're both in the s orbital, We've got M sub L with a 0, and then our spin here is indicated by a positive half and a negative half to show that they are opposite spins. Right? We have to have something different. They cannot have the same 4 quantum numbers and exist. Just can't do it. So the sublevels in each principal energy shell of hydrogen all have the same energy as other single electron systems. We call orbitals with the same energy degenerate orbitals. For multi-electron atoms, the energies of the sublevels are split. This is caused by charge interaction, shielding, and penetration. And so the lower the value of the L quantum number, remember L is associated with the orbital shape, then the less energy the sublevel has. So here, our S, or L equals 1, is the lowest. Then we said P is the next lowest. That L equals 1. I think I said L equals 1 here. Sorry, L equals 0. L equals 1 here. P is the next one, right? Then D is the next one. That's L equals 2. And then we've got F is final. That's L equals 3. So when we fill our orbitals with electrons, we fill from the lowest to the highest in energy. So S gets filled first in a principal energy level, then P, and then D, and then F. That is the Aufbau principle. Orbitals that are in the same sublevel have the same energy. So, like the 3 orbitals in the P sublevel, those are all equal in energy. All right, there is also a rule that says no more than 2 electrons per orbital. That is the Pauli exclusion principle. And then finally, when we are filling orbitals that have the same energy, we have to place 1 electron in each before we go and complete the pair. And that is called Hund's rule. All right, so the electron configuration is a listing of the sublevels in order of filling, with the number of electrons in that sublevel written as a superscript. So, krypton has 36 electrons. First, I fill the 1s orbital with its 2 electrons. Let me change colors here. Oh, no. Oh, no. Okay, never mind. I thought I could change the color of my pointer. All right, 1s, we fill it with its 2 electrons. Then we fill 2s with its 2 electrons. Then we fill 2p. Remember, it can hold 6 electrons, so I fill those 6 up. Then 3s gets its 2 electrons, etc., etc. So, in order of filling, you will recall, hopefully, that, and this is from a previous video. I'll put the link in the description because I think I have to do that. But anyway, I'll put the link. Hopefully you recall that the energy associated with the sublevel, once we get to a certain principal energy level, we start getting a weird order because, like, 3D is higher in energy than 4s, which we see indicated here. So we fill the 4s first, and then the 3D. There is also a shorthand way of writing an electron configuration. It is used just because sometimes, especially things with a lot of electrons, that is so much writing, and why? Just why? So the shorthand way of writing electron configuration is to use the symbol of the previous noble gas in square brackets, like these, to represent all of those inner electrons. And then just write the last bit of electrons, however many it is. So for rubidium, it has 37 electrons. Well, the previous noble gas is krypton here. So we could write the entire thing, and we just have 1 additional electron on top of these. So we could write it this way. Or we could take all of this and say, basically, all right, we got a krypton plus 1. So again, square brackets, noble gas, and then whatever's left over. So those are the 2 ways that we have to write the electron configurations. When we are drawing orbital diagrams, this is what they look like. So you have a box for each orbital in the sublevel, and then you fill it with your half arrows. When we get to having multiple orbitals in a sublevel, we have to put one electron with a parallel spin in each orbital, and then we can go back and double up. Right? So if I draw it up, got to draw this one up, I would have to draw this one up to draw the next one. Right? So our valence electrons are the electrons in all the sublevels with the highest within the highest principal energy shell. All right? So if I think back to that carbon, the second principal energy level was the highest that I had. So all of those are the valence electrons. Electrons in our lower energy shells are what we call our core electrons. And one of the most important factors in how we figure out how an atom behaves, chemically and physically, is the number of valence electrons that it has. Right? So here is part of the periodic table. We've got 1s1, 1s2. That's all we can hold in the s orbital. So then 2s1 comes next. 2s, that's our principal energy level 2. That means this is a valence electron, and all of the ones in a lower level, those are core electrons. Likewise, 3s1, this is principal energy level 3. That is a valence electron. All of the 2s and 1s are core electrons. Alright, so the group number corresponds to the number of valence electrons on the periodic table. And the length of each block on the periodic table is the maximum number of electrons that sublevel can hold. So it's a little hack for you. We'll look on it in the next slide. The period number, so which row it's in, corresponds to the principal energy level of the valence electrons. So let's look at that. Alright, so our period number tells us what principal energy level our valence electrons are in. Right? This chunk is where our s orbitals lie, and so s orbitals can hold 2 electrons. This chunk is 2 columns wide. P orbitals can hold 6 electrons. This chunk is p columns wide, 6 columns wide. This is our d orbital chunk. D orbitals can hold 10 electrons. This is 10 columns wide. And then F is this little chunk that goes down here. So we can use wherever it is as sort of coordinates to tell us what the electron configuration is. So in this case, chlorine is here. So I know that it is in row 3. So I know that my outermost electrons are in 3p. And I have 1, 2, 3, 4, 5 electrons in 3p. So that's how we use the periodic table to do that. This would be a really good way for you to sort of shortcut and double check yourself when it comes to writing electron configurations. All right, so irregular electron configurations. We know, because of sublevel splitting, that the 4s sublevel is lower in energy than the d orbital, 3d orbital. This is that video that I mentioned previously that I have linked for you. So go back and look at that if you don't remember. So the difference in energy is not large, but it matters. And some of the transition metals have irregular electron configurations in which the ends only, like we only partially fill the ns, so 4s, 5s, whatever, before we fill the n-1 d. So like 4s might only get 1 electron before we move on to 3d, for example. Therefore, the electron configurations of our transition elements are found experimentally because they are weirdos. Alright, so, for example, chromium. We expect it to be argon, then 4s2, and then 3d4. But what we actually get is 4s1, 3d5. Same for copper. We expect 3d9. We get 3d10 because we only put 1 there. Likewise for molybdenum, ruthenium, palladium. Electron configurations for transition metals are weirdos. It's not something that I will be asking in our course, but I expect you to be aware of it. Okay, so our properties are directly related to our electron configurations. And the properties of our elements follow a periodic pattern. We call that the periodic law. Elements in the same column have similar patterns or similar properties because of this pattern. And the reason for that is they all have the same number of valence electrons. So the quantum mechanical model explains this through the number of valence electrons and the types of orbital they occupy. And that is, a periodic function of the periodic table. So, for example, our noble gases all have 8 valence electrons, which we can see here. 2 plus 6, that's a total of 8, except for helium, which only has 2. Because that valence shell is full, they are non-reactive, fairly non-reactive, and helium and neon are pretty much inert, reacts with nothing, right? And so the reason the noble gases are so non-reactive is because that electron configuration is especially stable. Alkali metals, on the other hand, have 1 more electron than the previous noble gas. So they've got 1 electron and they're trying to lose it, and therefore they are actually very reactive. So here you can see 2s1, 3s1, 4s1. So we've got that 1 valence electron for all of these. So what happens is, to become that stable noble gas electron configuration, we lose that electron. So our alkali metals form a 1+ charge. Halogens have 1 fewer electron than the next noble gas. So they want to become like that noble gas. They want to gain an electron. Again, with the goal, I say goal, they don't think about it, but with the goal of becoming just like that next noble gas. So here you can see we got 7 valence electrons. We gain an electron and become an anion to gain that stability. So in their reactions with nonmetals, they tend to share electrons so that everybody can get the electron configuration of noble gases. So we've seen that many metals and nonmetals form 1 specific ion and that the charge is predictable based on their position on the periodic table. Group 1A is 1+, Group 2A is 2+, 7A is 1-, Group 6A is 2-. These atoms form ions specifically to result in an electron configuration that is the same as the nearest noble gas. That's very important. That is the whole point of bonding. We want to become more stable. All right, so here we can see these are the predictable charges. You should already have these columns labeled on your periodic table. So, anions are formed when nonmetal atoms gain enough electrons to have 8 valence electrons. So what they're doing is they're filling up their S and P sublevels in their valence shell. A sulfur atom has 6 valence electrons. When it bonds and becomes the sulfur anion, it has gained 2 electrons, and now you can see here we've got 3s2, 3p6. That's a total of 8 valence electrons. Likewise, our cations are formed when a metal atom loses all the valence electrons, resulting in a new, lower energy valence shell. So, this process is always endothermic. And what we have is magnesium that has 2 valence electrons and 3s. Then it loses those valence electrons and becomes the magnesium cation, which looks just like the previous noble gas, neon. Notice our 3s is gone now. All right, so here again, the goal is to get like the nearest noble gas. So for aluminum, there are 3 valence electrons. They would be here, and then we get rid of them. So we drop down to the electron configuration of neon. All right, transition metals are different and are weirdos. When our transition metals form cations, the first electrons removed are the valence electrons, even though there were other electrons added after them. So, yeah. And then electrons can also be removed from the sublevel closest to the valence shell after the valence electrons. So, let's look at an example. All right. Iron has 2 valence electrons. Valence electrons are always the highest number principal energy level. We filled these first because they were lower in energy, but they're still the valence electrons. Okay? So, when iron forms a cation, it first loses its valence electrons. So we go from having 2 electrons in 4s to now not having 2 electrons in 4s. Then, if it becomes a 3+ cation, then we could lose an electron from that d orbital here and become this. This is where our conversation is going to shift to magnetism. All right, magnetic properties associated with our transition metals specifically have to do with the electron configuration and the orbital diagrams, right? Electron configurations that result in unpaired electrons mean that atom or ion has a net magnetic field. We call that paramagnetism. So, they are going to be attracted to a magnetic field. Paramagnetic elements are magnetic. Not paired, paramagnetic. That seems a little backwards because we're saying not paired, but please put that in your brain. Then likewise, electron configurations where we have all paired electrons means that it's not going to respond to a magnetic field. We call that diamagnetism. They are slightly repelled by a magnetic field. So paramagnetic, this is our magnetic stuff, like iron. In the previous slide, actually I'll put it on the next slide here. And then diamagnetism is if we are all paired. So, like I said on the previous slide, like iron, if we have unpaired electrons, what that means is we're going to have basically uncanceled out electron spins. And this is what contributes to the magnetism of our elements like iron. Iron is magnetic. This is why.